There's a place in the cosmos so strange, so utterly baffling, that it makes even the most brilliant scientists question everything they know about gravity. Picture this, a vast, silent expanse between galaxies, where the usual rules of the universe seem to flip upside down. Instead of pulling objects together, gravity here does the unthinkable. It pushes them apart. This isn't science fiction. This is the empty zone, one of the most mysterious regions in existence, where the fabric of reality itself behaves in ways we can't yet explain. What if I told you that everything we thought we knew about how gravity works might be incomplete? In these desolate stretches between galaxies, something extraordinary happens. The force that holds planets in orbit, that keeps your feet on the ground, suddenly reverses direction. It's as if the universe has hidden a secret switch, flipping gravity's pull into a push. Scientists call it gravitational reversal, and it's one of the biggest unsolved puzzles in modern astrophysics. Could this be a clue to dark energy, the enigmatic force accelerating the expansion of the universe? Or is there something even more bizarre at play, something beyond our current understanding? This is more than just a cosmic curiosity. It's a frontier that could redefine physics as we know it. Think about it. If gravity can behave so unpredictably in these empty zones, what else might we be missing? The implications are staggering, touching everything from the fate of the universe to the very nature of space and time. Today, we're embarking on a journey into the heart of this mystery, peeling back the layers of the unknown to uncover what really happens in those eerie voids between galaxies. Buckle up, because what we're about to explore will challenge your perception of reality itself. The empty zone isn't just an absence of stars or galaxies, it's a cosmic anomaly where the very fabric of space defies expectations. Picture a desert so vast it makes the Sahara look like a grain of sand, stretching across hundreds of millions of light years with barely a speck of matter in sight. Yet within this eerie nothingness, gravity doesn't just vanish. Instead, it twists into something unrecognizable. Normally, gravity pulls objects toward mass, like planets orbiting a star or apples falling to Earth. But in these voids, something strange happens. The gravitational force seems to repel rather than attract. It's as if the universe has hidden pockets where the rules are rewritten, and scientists are scrambling to decode them. Why does this matter? Because these empty zones might hold the key to one of astrophysics' biggest mysteries, dark energy. This invisible force is driving the universe's expansion at an accelerating rate, and the bizarre gravitational behavior in voids could be a clue to how it works. Imagine blowing up a balloon with dots on its surface. The dots represent galaxies, and as the balloon inflates, they move apart. But in the empty zones, it's as if someone's tugging the balloon's rubber outward, stretching it faster than anywhere else. That extra pull could be dark energy's fingerprint, warping gravity itself. But there's another possibility, one that's even more mind-bending. What if these voids aren't truly empty? What if they're filled with something we can't see or detect yet? Some theories suggest exotic particles or hidden dimensions might be at play, subtly altering gravity in ways we don't yet understand. Think of it like an invisible current in the ocean. You can't see it, but it reshapes everything in its path. If that's true, then these so-called empty zones might be teeming with secrets, waiting to rewrite our understanding of the cosmos. The more we study these voids, the clearer it becomes. They're not just blank spaces. They're dynamic, enigmatic regions where the universe tests its own rules. And every new discovery, whether it's a flicker of unexpected radiation or a subtle warp in space-time, brings us closer to unraveling the mystery. So the next time you look up at the night sky, remember, between those glittering stars and galaxies lies a hidden frontier where gravity itself dances to an unknown tune. Gravity is supposed to be the universe's great unifier, the silent hand that sculpts galaxies, keeps planets in orbit, and pins us to the ground. Yet in the empty zones between galaxies, it breaks its own rules. Imagine tossing a ball into the air only for it to shoot away faster instead of falling back down. That's the kind of cosmic defiance we're dealing with here. Newton's laws, which have reliably described gravity for centuries, crumble in these voids. Even Einstein's theory of general relativity, our gold standard for understanding spacetime, doesn't fully account for this bizarre repulsion. It's as if the universe has a hidden rulebook and we've only just stumbled upon a torn-out page. So what could be causing this gravitational rebellion? One leading suspect is dark energy, the enigmatic force accelerating the universe's expansion. Think of it like an invisible wind, relentlessly pushing galaxies apart. In the empty zones where matter is scarce, dark energy's influence might overpower gravity's usual pull, flipping its effect entirely. It's a bit like blowing on a dandelion. The lighter the seeds, the easier they scatter. But here's the twist. If dark energy is the culprit, why doesn't this reversal happen everywhere? Why only in these vast, matter-starved deserts? That inconsistency has scientists digging deeper, questioning whether dark energy alone can explain the phenomenon. Then there's the wild-card possibility, hidden dimensions. Some theories suggest our universe might be brushing up against unseen realms, warping gravity in ways we can't yet measure. Picture a sheet of paper with tiny, invisible folds. Just because we can't see them doesn't mean they're not affecting how things move across the surface. If extra dimensions exist, they could be subtly distorting gravity in the empty zones, turning attraction into repulsion. Even more mind-bending is the idea of exotic particles, unknown forms of matter that don't interact with light, slipping through our detectors unnoticed. These phantom particles could be saturating the voids, creating a gravitational push where we'd expect a pull. Whatever the explanation, one thing's clear: this anomaly is more than a cosmic oddity. It's a crack in the foundation of physics, revealing how much we still don't understand about the forces shaping our universe. Every telescope pointed at these voids, every simulation run, brings us closer to rewriting the laws we once thought were set in stone. And that's the thrilling part. Science isn't about having all the answers. It's about discovering where the rules break, because that's where the next great revelation lies. Dark energy might just be the universe's greatest enigma, an invisible force so dominant it shapes the fate of everything we see, yet remains frustratingly elusive. Picture a cosmic tug-of-war where one side has an unbeatable advantage. On one end, gravity tries to pull matter together, forming galaxies and clusters. On the other, dark energy relentlessly pushes, stretching spacetime itself. And in the empty zones between galaxies, where matter is almost absent, dark energy doesn't just win, it dominates completely. That's why these voids behave like cosmic repulsion zones, as if space itself is exhaling, shoving galaxies even farther apart. But here's the puzzle. If dark energy is everywhere, why does its push overpower gravity only in these vast, desolate regions? The answer lies in density, or rather, the lack of it. Imagine a crowded room where everyone's chatting. The noise blends into a dull roar, and no single voice stands out. Now step into an empty hallway. Suddenly, even a whisper echoes loudly. In the same way, where matter is sparse, dark energy's subtle push becomes unmistakable. Galaxies aren't being repelled by some mysterious anti-gravity. They're simply less anchored, more easily swept up in dark energy's cosmic tide. Yet this explanation raises even bigger questions. If dark energy's influence varies based on the density of matter, could it hint at something deeper about its true nature? Some theories suggest dark energy isn't a constant force but a dynamic one, changing over time or space. Think of it like a thermostat. Sometimes it cranks up the heat, other times it cools things down. If that's true, then the empty zones aren't just passive bystanders. They're active laboratories, revealing how dark energy behaves when it's unimpeded. And then there's the elephant in the room. What is dark energy really? Is it a property of space itself, as Einstein's cosmological constant suggested? Or could it be something far stranger, like a new kind of field or particle we've yet to discover? The empty zones might hold the key. By studying how gravity reverses in these voids, scientists could uncover clues about dark energy's origins, clues that might rewrite our understanding of physics. One thing's certain, the more we learn about these mysterious regions, the more we realize how much we don't know. Dark energy isn't just a placeholder for our ignorance. It's a call to explore, to question, and to rethink the very fabric of reality. And as telescopes peer deeper into these cosmic deserts, who knows what other surprises might be lurking in the silence? Dark matter and dark energy are like the yin and yang of the cosmos. One pulls, the other pushes, shaping the universe in ways we're only beginning to grasp. But in the empty zones, this delicate balance is thrown off entirely. While dark matter's gravitational grip helps hold galaxies together, its absence in these vast voids leaves dark energy unchecked, like a runaway train with no brakes. That's why these regions behave so strangely. Without dark matter's anchoring force, the repulsive push of dark energy takes over, flipping gravity's script. So why is dark matter missing from these cosmic deserts? The answer might stretch back to the universe's earliest moments. Picture the newborn cosmos as a lumpy soup of matter and energy. Where the soup was thickest, dark matter clumped together, eventually pulling in gas and dust to form galaxies. But in the thinner patches, the future empty zones, dark matter never gained a foothold. Over billions of years, as the universe expanded, these underdeveloped regions stretched into the colossal voids we see today. It's like blowing bubbles in batter. Where the bubbles pop, you're left with gaps, no structure, no dark matter, just empty space. Here's where it gets even stranger. Dark matter isn't just absent in these voids, it's actively avoided. Simulations show that as galaxies formed, dark matter was funneled into dense filaments, a cosmic web connecting clusters like threads in a tapestry. The empty zones, they're the holes in that web. Without dark matter's gravitational scaffolding, normal matter, the stuff we can see, had no reason to stay, leaving behind a near-perfect vacuum. This absence might be the missing clue to the empty zone's gravitational rebellion. Think of dark matter as the glue that keeps gravity's pull intact. Remove it and dark energy's push runs wild. But that raises another question. If dark energy is everywhere, why doesn't it overpower gravity in places with more matter? The difference comes down to competition. In galaxy clusters, dark matter's pull is strong enough to resist dark energy's push. But in the voids where dark matter is MIA, there's nothing to fight back. The implications are staggering. If we can map how dark matter distributes or doesn't across these voids, we might finally crack the code of dark energy's true nature. It's like solving a cosmic murder mystery. The absence of dark matter isn't just a curiosity. It's the fingerprint of something far bigger at work. And with every new observation, we're one step closer to understanding the invisible forces rewriting the rules of gravity itself. The universe isn't a chaotic scatter of galaxies, it's a masterpiece of intricate design. woven together by an invisible framework known as the cosmic web. Picture a spider's silk stretched across billions of light years, its threads glittering with galaxies while the gaps between them yawn into darkness. These threads or filaments are the universe's backbone, dense highways of matter where galaxies cluster like cities along a freeway. But between them lie the voids, the empty zones, where gravity's rules seem to unravel. Why does this cosmic architecture matter? Because it's the key to understanding why gravity flips its script in these desolate regions. During the universe's infancy, tiny ripples in the fabric of space-time seeded the growth of this web. Where matter was slightly denser, gravity pulled more gas and dark matter into clumps, eventually forming galaxies. But in the thinner patches, matter never stood a chance. Over eons, these underdeveloped stretches expanded into the colossal voids we see today, left behind like empty lots in a bustling metropolis. Here's the twist: the cosmic web isn't just a map of where matter is, it's also a record of where it isn't. The voids aren't random accidents, they're fossils of the universe's earliest moments, their emptiness telling a story about how gravity sculpted the cosmos. In the dense filaments, gravity's pull is unmistakable, binding galaxies into clusters and superclusters. But in the voids, where matter is vanishingly sparse, there's nothing to anchor gravity's usual behavior. Instead, the relentless push of dark energy takes over, stretching these regions even farther apart. It's like a tug of war where one team never shows up, the outcome is inevitable. This grand structure doesn't just explain where gravity reverses, it hints at why. The cosmic web reveals how the universe's large-scale imbalances create pockets where the rules bend. Think of it like Earth's oceans. The tides follow predictable rhythms near shorelines, but in the open deep, currents move in unexpected ways. Similarly, gravity's reversal in voids isn't a glitch, it's a consequence of the cosmos's uneven terrain. And the implications go even deeper. By studying the cosmic web, scientists can trace how dark energy and dark matter have shaped the universe over billions of years. The filaments act like cosmic scales, weighing the tug of dark matter against the push of dark energy. But the voids, they're the control group, a place where dark energy operates without interference, offering a pristine lab to study its true nature. Every void is a window into the forces that govern existence itself, a silent testament to the universe's hidden blueprints. So the next time you hear about the cosmic web, remember, it's more than just a pretty metaphor. It's the universe's skeleton, holding everything together while revealing the secrets of its emptiest corners. And as we peel back its layers, we're not just mapping space, we're decoding the very rules of reality. Einstein's theory of general relativity paints gravity as the bending of spacetime itself, a cosmic trampoline where massive objects like stars and planets create dips that pull everything toward them. It's an elegant idea that's held up for over a century, explaining everything from black holes to the orbit of Mercury. But step into the empty zone, and this elegant framework starts to fray at the edges. Here, where gravity seems to repel rather than attract, relativity's equations struggle to make sense of the chaos. It's like using a weather model designed for calm skies to predict a hurricane. The tools just aren't built for the extremes. Meanwhile, quantum mechanics operates on a completely different playing field. It's the rulebook for the subatomic world, where particles pop in and out of existence and forces like electromagnetism dominate. Gravity, in quantum terms, it's practically a ghost too weak to even register on the particle scale. Yet in the empty zone where matter is nearly absent, quantum effects might play an outsized role. Some theories suggest virtual particles, fleeting quantum fluctuations, could be bubbling up in these voids, subtly tweaking gravity's behavior. Imagine a quiet room where even a whisper echoes. In the void's near-perfect vacuum, quantum whispers might amplify into shouts, warping gravity in ways relativity can't explain. This isn't just a minor disagreement between two theories. It's a full-blown cosmic standoff. Relativity says space-time is smooth and continuous like a stretched sheet. Quantum mechanics insists everything is granular, a seething foam of tiny, discrete bits. In most of the universe, their differences don't matter, they operate in separate realms. But the empty zone forces them into the same ring, and neither theory comes out unscathed. It's as if you tried to measure a painting with a microscope or a galaxy with a ruler. The tools don't fit the problem. That's why these voids are more than just cosmic oddities. They're battlegrounds where the deepest laws of physics collide, revealing gaps in our understanding. Scientists have long dreamed of a theory of everything that bridges relativity and quantum mechanics, something like string theory or loop quantum gravity. But math alone won't solve this puzzle. We need real-world observations, and the empty zones offer a perfect laboratory. Their gravitational anomalies might be the Rosetta Stone, decoding how these two theories stitch together at the edges of reality. What's at stake? Nothing less than a complete rewrite of physics. If we can crack why gravity reverses in these voids, we might finally unify the forces that govern the universe. Picture it like finally seeing the full image in a fractured mirror. Every piece we place changes how we understand the whole. And that's the thrill of science. The answers aren't just hidden in the light of stars, but in the darkness between them. While dark energy remains the leading explanation for gravity's bizarre behavior in the empty zones, it's far from the only game in town. Some scientists argue we're looking at the problem backward. What if gravity itself isn't working the way we think? Enter MND, or modified Newtonian dynamics, a radical idea that suggests gravity doesn't fade with distance as Newton's laws predict. Instead, in places where matter is scarce, like those vast cosmic voids, gravity weakens in unexpected ways. Picture a flashlight beam. Normally, it dims steadily as you move away. But under MND, the beam might flicker unpredictably in the dark, behaving differently when there's nothing around to reflect its light. This could explain why galaxies at the edges of these voids seem to drift apart as if pushed by an invisible hand, without invoking dark energy at all. Then there's quintessence, a theory that turns dark energy from a static force into something far more dynamic. Unlike the steady push of Einstein's cosmological constant, quintessence suggests dark energy ebbs and flows, evolving over time like a cosmic heartbeat. Imagine blowing up a balloon, but instead of inflating at a constant rate, it sometimes expands faster or slower, as if guided by an unseen rhythm. In the empty zones where matter's grip is weakest, these fluctuations might amplify, creating pockets where gravity's pull briefly turns into a nudge. It's a tantalizing idea, one that could explain why the universe's expansion isn't perfectly uniform, with some voids stretching faster than others, but the alternatives get even wilder. Some researchers toy with the idea of phantom energy, a hypothetical form of dark energy so potent it could eventually tear space-time apart. Others explore brain-world cosmologies, where our universe is just one slice of a higher dimensional reality, and gravity's odd behavior in voids is a ripple from neighboring dimensions. Think of it like a sheet of paper vibrating in the wind. What we perceive as gravity's reversal might just be the shadow of forces we can't yet see. What's fascinating isn't just the diversity of these theories, but what they reveal about science itself. Every time a mainstream idea hits a snag, like gravity's defiance in the voids, it sparks a frenzy of creativity, pushing researchers to question the foundations of physics. Whether manned, quintessence, or something even stranger wins out, one thing's certain: the empty zones aren't just empty, they're cosmic chalkboards scrawled with equations we're only beginning to decipher. And the answers we find there might not just solve a local mystery, they could rewrite the rules for the entire universe. In 2017, astronomers stumbled upon something that sent shockwaves through the astrophysics community, a colossal region of space they dubbed the Great Repeller. Unlike anything we'd seen before, this mysterious expanse wasn't just empty. It seemed to be actively pushing our Milky Way galaxy away, as if space itself had a hidden force field. What made this discovery so startling wasn't just the repeller's existence. It was the realization that the voids between galaxies might not be passive after all. Instead of mere blank spaces, they could be dynamic actors on the cosmic stage, shaping the motion of entire galaxies across mind-boggling distances. So how does a void, a place where matter is almost non-existent, exert such influence? Think of it like a cosmic game of tug-of-war. Normally, galaxies are pulled toward dense regions of the universe where massive clusters act like gravitational magnets. But the Great Repeller flips this script. Instead of attracting, it appears to repel, creating a bizarre push-pull dynamic that defies intuition. One theory suggests it's not the void itself doing the pushing, but the absence of matter around it. Imagine standing in a crowded room where everyone's leaning toward a popular speaker. If you step into an empty corner, the crowd's collective pull might make it seem like the corner is pushing you away, even though it's just the imbalance of forces at work. Here's where things get even stranger. The Great Repeller isn't just some isolated phenomenon. It's part of a much larger pattern, a cosmic dance where galaxies move not just toward attraction but away from emptiness. This could mean that the empty zones we've been exploring aren't just curiosities, they're integral to the universe's structure, playing an active role in how galaxies drift and cluster. Some researchers even speculate that these repelling regions might be intertwined with dark energy, amplifying its effects in ways we don't yet understand. But the Great Repeller raises as many questions as it answers. If voids can push galaxies, does that mean gravity's reversal isn't just a local oddity but a universal feature? Could there be other repellers out there, hidden in the darkness between superclusters, subtly steering the motion of everything around them? The more we study these phenomena, the clearer it becomes. The universe isn't just a collection of stars and galaxies. It's a dynamic, ever-shifting web where even the emptiest places hold unimaginable power. And if we can decode their secrets, we might finally understand the invisible forces that have been shaping cosmic history all along. Supercomputers have become the time machines of astrophysics, letting scientists rewind the universe's history to test what might be happening in those enigmatic empty zones. Imagine feeding trillions of data points into a machine, the distribution of galaxies, the pull of dark matter, the push of dark energy, and watching as it reconstructs 14 billion years of cosmic evolution in weeks. These simulations reveal something startling. Voids don't just happen randomly. They emerge from the universe's earliest fluctuations, growing like bubbles in boiling water as space expands. And within them, gravity's strange reversal isn't a glitch, it's a predictable outcome of the cosmic recipe. Yet there's a catch. When researchers compare these digital universes to the real one, something doesn't quite match. The voids in simulations often appear smaller or less extreme than those we observe, as if the models are missing a key ingredient. It's like baking a cake that looks perfect on the outside but collapses when you slice it. The texture isn't right. Some suggest the discrepancy lies with dark energy's behavior. Maybe it's stronger in real voids than simulations assume, or perhaps it interacts with dark matter in ways we haven't programmed. Others wonder if the simulations underestimate the universe's initial lumpiness, those tiny density variations that seeded the cosmic web. Here's where things get even more intriguing. Some of the latest models introduce wildcards, exotic particles, tweaks to gravity's laws, or even quantum effects bubbling up in the emptiness. One simulation might test Mann predictions, while another explores phantom energy's explosive potential. Each run is like a parallel universe trial, revealing which theories hold up and which crumble under scrutiny, and when a simulation finally mirrors reality. That's when the real breakthroughs happen, but simulations alone won't solve the mystery. They're just one piece of the puzzle, cross-checked against telescope observations and gravitational wave detections. Every mismatch between model and reality isn't a failure. It's a clue pointing toward physics we've yet to uncover. The empty zones aren't just cosmic oddities. They're proving grounds, challenging us to think bigger, dig deeper, and rewrite the rules until the simulation finally matches the sky. Studying the empty zones of the universe is like trying to photograph a shadow. It's not just the absence of light that makes it difficult, but the sheer scale of nothingness itself. These voids sprawl across hundreds of millions of light years, so vast that even light from distant galaxies gets stretched into near invisibility by the time it reaches us. Traditional telescopes, designed to focus on bright, dense objects like stars and galaxies, often struggle to capture meaningful data from these desolate regions. It's like using a flashlight to search for a single grain of sand in a desert. The tool isn't built for the task. That's where instruments like the Hubble Space Telescope come in. Orbiting above Earth's distorting atmosphere, Hubble has peered into the depths of these voids, capturing faint glimmers of radiation or the subtle warping of light from background galaxies, hints that something invisible might be at work. But Hubble is just the beginning. The James Webb Space Telescope, with its infrared eyes, can detect even fainter signals, piercing through cosmic dust to study the void's structure in unprecedented detail. Think of it as swapping out a magnifying glass for an electron microscope. Suddenly, the invisible becomes tangible. Yet even with these technological marvels, the void remains a formidable puzzle. One major hurdle is the sheer emptiness itself. With so little matter to interact with, gravitational effects are subtle, like trying to measure the weight of a feather in a hurricane. Scientists often rely on indirect methods, such as tracking how light bends around these regions, or mapping the faint echoes of the cosmic microwave background, the afterglow of the Big Bang. These techniques are like listening for whispers in a silent room. The slightest distortion could reveal volumes about what's hiding in the dark, another challenge. Time, the universe's expansion, means light from the deepest voids takes eons to reach us, offering a snapshot of the past, not the present. By the time we observe a void, it might have evolved in ways we can't yet predict. It's like receiving a letter mailed billions of years ago. The story it tells is incomplete, missing the latest chapters. But perhaps the most tantalizing obstacle is the void's unpredictability. Unlike galaxies, which follow relatively orderly patterns, these empty zones seem to play by their own rules. One void might exhibit strong gravitational repulsion, while another, seemingly identical, shows no such effect. This inconsistency forces scientists to question whether they're dealing with a universal phenomenon or a collection of cosmic exceptions. Every breakthrough, no matter how small, chips away at the mystery. A flicker of unexpected radiation here, a peculiar distortion there. Each clue is a piece of the puzzle, slowly revealing the void's hidden mechanics. And as technology advances, so does our ability to probe deeper, pushing the boundaries of what we know. The void may guard its secrets well, but with every observation, we're learning how to listen. The Hubble tension isn't just a minor disagreement among scientists, it's a full-blown cosmic crisis that threatens to upend our understanding of the universe's expansion. On one side, we have meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang, suggesting the universe is expanding at a certain rate. On the other, observations of nearby stars and supernova tell a different story, insisting the expansion is significantly faster. The discrepancy isn't a small rounding error. It's a gap large enough to suggest something fundamental is missing from our models. And here's where the empty zones come in. These vast, gravity-defying voids might be the wild card no one saw coming, quietly tilting the cosmic scales in ways we're only beginning to grasp. Picture the universe as a stretchy fabric with galaxies sewn into its surface. In dense regions where matter clusters together, gravity's pull tugs at the fabric, slowing expansion like a weight on a rubber sheet. But in the empty zones where gravity seems to reverse, the fabric behaves differently. It's as if invisible hands are pulling it apart from within. If these voids exert a net repulsive effect, they could be acting like cosmic accelerators, subtly speeding up expansion in their vicinity. That might explain why local measurements, which include the influence of nearby voids, show a faster rate than the pristine, averaged view of the early universe. It's like measuring the speed of a river while standing in a whirlpool. The local currents don't match the broader flow, but the plot thickens. Not all voids are created equal. Some are older, larger, and emptier, while others are smaller and still evolving. This variation means their impact on expansion isn't uniform. Imagine blowing bubbles in a pot of syrup. Some pop quickly, while others linger, each affecting the liquid's surface tension differently. Similarly, voids might distort spacetime unevenly, creating pockets where dark energy's push is amplified or dampened. If we've underestimated this variability, it could resolve the Hubble tension by revealing that expansion isn't a single, universal speed, but a mosaic of rates shaped by the void's hidden architecture. There's another twist: time. The universe's expansion hasn't been constant. It's accelerated over billions of years, driven by dark energy. But what if voids played a role in that acceleration? In the early universe, when matter was more evenly distributed, their gravitational push might have been negligible. But as the cosmic web formed and voids grew, their cumulative influence could have tipped the scales like a snowball rolling downhill. This wouldn't just explain the Hubble tension, it could rewrite the story of how dark energy itself came to dominate the cosmos. The implications are staggering. If voids are secretly steering the universe's expansion, then our entire cosmic timeline might need adjusting. Suddenly, the Hubble tension isn't just a problem, it's a clue, pointing toward a deeper layer of physics where gravity, dark energy, and emptiness intertwine in ways we've barely imagined. And that's the beauty of cosmology. The biggest mysteries often lurk in the places we least expect, waiting to transform our understanding of everything. Even in the deepest voids of the cosmos, where galaxies are few and far between, space is never truly empty. According to quantum mechanics, what we perceive as nothingness is actually a bubbling, seething sea of energy, a quantum foam where particles flicker in and out of existence in fractions of a second. These fleeting disturbances, known as quantum fluctuations, might hold the key to one of the most perplexing mysteries in physics: gravity's bizarre reversal in the empty zones. Think of the quantum vacuum like a pot of water simmering on low heat. At first glance, the surface appears calm, but look closer, and you'll see tiny bubbles constantly forming and popping. In the same way, empty space is anything but tranquil. Virtual particles, pairs of matter and antimatter, materialize for the briefest moments before annihilating each other, leaving behind a faint but measurable energy. This vacuum energy isn't just theoretical. It's been detected in lab experiments like the Casimir effect, where two metal plates placed microscopically close together feel a slight push from these quantum whispers. Now imagine this same phenomenon playing out on a cosmic scale. In the vast emptiness between galaxies where matter is almost absent, vacuum energy might dominate the scene. Normally, its effects are drowned out by the gravitational pull of stars, planets, and dark matter. But in the voids where there's little to compete with it, vacuum energy could subtly warp spacetime, tweaking gravity's behavior in ways we don't yet understand. Some theories suggest these quantum ripples might amplify dark energy's repulsive push, flipping gravity's pull into a nudge. Others propose that vacuum energy itself could generate a kind of anti-gravity effect, bending the rules of relativity in extreme environments. The implications are staggering. If quantum fluctuations can influence gravity on such massive scales, it would bridge two seemingly incompatible worlds, the infinitesimally small realm of quantum mechanics and the vast expanse of cosmology. Picture it like discovering that tiny ripples in a pond can somehow alter the course of an ocean current. That's the level of paradigm shift we're talking about, a revelation that could rewrite our understanding of how the universe holds together. Of course, this idea is still speculative. Vacuum energy is notoriously difficult to measure, and its effects in voids are even more elusive. But the mere possibility opens doors to radical new physics. Could the empty zones be cosmic laboratories, revealing how quantum mechanics and gravity intertwine in ways Einstein never imagined? As telescopes peer deeper into these desolate regions, and experiments like gravitational wave detectors grow more sensitive, we might finally catch a glimpse of the quantum vacuum's hidden role in shaping the cosmos. And if we do, it won't just solve the mystery of gravity's reversal, it could unveil a deeper layer of reality, one where even the emptiest corners of space hum with invisible energy. Black holes are the universe's ultimate anchors, cosmic pits of gravity so intense they bend spacetime itself, holding entire galaxies in their grip. From the supermassive beasts at the heart of galaxies to the smaller, stellar mass remnants scattered like cosmic debris, these gravitational monsters shape the universe in ways we're only beginning to understand. But step into the empty zone and something's missing. Black holes here are vanishingly rare, as if the void itself has erased them. And that absence might be the missing clue to why gravity behaves so strangely in these desolate regions. Think of black holes like knots in a vast cosmic net, where they cluster in galaxies and dense filaments of the cosmic web. They pull everything tighter, reinforcing the structure of the universe. But in the voids where matter is sparse, black holes are almost non-existent. It's not just that there are fewer stars to collapse into black holes. It's as if the void's very nature prevents them from forming or surviving. Some theories suggest that in these regions, the gravitational environment is so unusual that black holes either get ejected or evaporate over time, like ice cubes left in the sun. Without their anchoring presence, the void's delicate balance tips, allowing dark energy's push to dominate unchallenged. Here's where it gets even more intriguing. Black holes don't just sit quietly, they are active players in cosmic evolution. Supermassive black holes, in particular, spew out jets of energy and matter, shaping their surroundings for millions of light years. In dense regions, this feedback helps regulate star formation and keeps galaxies in check. But in the void, with no black holes to stir the pot, matter drifts aimlessly, never coalescing into new structures. It's like a forest where the tallest trees have been removed without their roots. The ecosystem collapses. The void's emptiness might not just be a coincidence. It could be a direct result of this missing black hole influence. But could the relationship go both ways? Some cutting-edge models suggest black holes might not just be absent in voids, they could actively avoid them. As the universe expands, black holes and galaxies migrate toward denser regions, drawn by gravity's pull like moths to a flame. Over billions of years, this migration leaves the voids behind, not just empty but actively drained of their gravitational anchors. It's as if the cosmos has a sorting mechanism, funneling black holes into the cosmic web while the voids grow ever lonelier. This isn't just a curiosity, it's a potential game-changer for understanding the universe's large-scale structure. If black holes play a role in shaping voids, then their absence could explain why gravity reverses in these regions. Without their counterbalancing pull, dark energy's repulsive force runs wild, stretching the void faster and farther than anywhere else. It's like removing the weights from one side of a scale. Suddenly, the other side shoots up. The implications are profound. If we can map the distribution of black holes across the cosmos, especially in the fringes near voids, we might finally crack the code of why these regions defy gravity's rules. Every missing black hole is a breadcrumb, leading us closer to understanding how the universe's most enigmatic forces interact. And that's the beauty of cosmology. Sometimes the most revealing clues aren't found in what's there, but in what's conspicuously absent. If gravity flips its script in the empty zones, what happens to time itself? Einstein showed us that clocks tick slower near massive objects like black holes or neutron stars, where gravity's pull warps spacetime into a steep slope. But in the voids where gravity's rules invert, time might play by a completely different set of rules. Imagine a clock placed deep inside one of these desolate regions. Instead of slowing down, could it actually speed up? The idea sounds like science fiction, but the math suggests it's not just possible, it might be inevitable. Here's why. According to general relativity, time dilation isn't just about gravity's strength, it's about spacetime's curvature. Near a massive object, spacetime bends inward, creating a gravitational well that drags time to a crawl. But in the empty zones where dark energy's repulsive push dominates, spacetime might curve outward, like the peak of a hill rather than the bottom of a valley. On that hill, time wouldn't be dragged down, it'd be propelled forward, ticking faster than anywhere else in the universe. Picture two clocks, one in a dense galaxy, the other in a void. Over billions of years, the void's clock could race ahead, accumulating extra seconds, minutes, even entire epochs compared to its galactic counterpart. This isn't just theoretical musing. Astronomers have already spotted hints of anomalous timekeeping in cosmic voids. Distant supernova exploding stars used as cosmic stopwatches appear to burn slightly brighter and longer in these regions, as if time itself is stretching differently there. It's like watching two candles burn in separate rooms. One flickers steadily while the other flares unpredictably, defying expectations. Could this be evidence of time speeding up in the voids? The data is still tentative, but the implications are staggering. If confirmed, it would mean time isn't just relative, it's location-dependent, shaped by the invisible tug of war between gravity and dark energy. But the real mind-bender is this. If time flows faster in voids, does that mean the universe ages unevenly? Imagine a patch of space where billions of years pass in what feels like moments elsewhere. Galaxies on the void's edge might evolve faster, their stars burning out sooner, their black holes merging earlier, all while the rest of the cosmos lags behind. It's a cosmic version of time zones, but instead of hours, the gaps could span eons. And here's where things get even stranger. If time dilation flips in voids, it could rewrite our understanding of causality, the fundamental rule that cause precedes effect. Normally, relativity preserves this order, but in regions where time accelerates, could events blur or even reverse? It's a stretch, but some theorists speculate that extreme time warps in voids might create pockets where the future influences the past, like ripples in a pond flowing backward. Of course, this is frontier science, riddled with unknowns. Time's behavior in voids might not be as dramatic as these thought experiments suggest, but the mere possibility forces us to confront how little we truly grasp about spacetime's flexibility. The voids aren't just empty spaces they're timekeepers, they're silent expanse holding clues to one of physics' deepest mysteries. And as we peer deeper into their darkness, we might find that time, like gravity, is far weirder than we ever imagined. The empty zones between galaxies might be more than just gaps in the cosmic web. They could be ancient relics, frozen echoes of the universe's explosive infancy. Picture the moment after the Big Bang, when the entire cosmos underwent a growth spurt so violent it defies comprehension. In less than a blink of an eye, space itself expanded faster than light, stretching from subatomic scales to astronomical proportions. This was cosmic inflation, and its fingerprints might still be visible in the voids we see today. How? Think of inflation like blowing up a balloon with tiny wrinkles on its surface. As the balloon inflates, those wrinkles stretch out, some smoothing away while others grow into larger creases. In the same way, minuscule quantum fluctuations from the universe's first moments could have been magnified by inflation, seeding regions of slightly higher and lower density. The denser patches eventually collapsed into galaxies and clusters, while the underdense regions ballooned into the vast voids we now observe. It's as if the empty zones are cosmic stretch marks, permanent imprints of the universe's rapid expansion. But here's the twist: inflation wasn't perfectly uniform. Some theories suggest it might have happened in fits and starts, creating bubbles of space that expanded at different rates. If true, the largest voids could be these primordial bubbles, regions where inflation lasted a fraction longer, stretching space thinner than anywhere else. Imagine a loaf of raisin bread baking unevenly. Some pockets end up airier with fewer raisins clustered together. In cosmic terms, those airy pockets are the voids, their emptiness a direct consequence of the universe's turbulent birth. This isn't just speculation. The cosmic microwave background, the afterglow of the Big Bang, shows faint temperature variations that align eerily with the distribution of voids today. Cooler spots in this ancient light might trace back to those underdense regions, their subtle shadows preserved like fossils in the sky. By mapping these patterns, scientists can peer back in time, reconstructing how inflation sculpted the cosmos. It's like analyzing the rings of a tree to deduce the weather conditions centuries ago, except here, the tree is the universe and the rings are its voids. The implications go even deeper. If voids are indeed fossils of inflation, they could reveal secrets about the mysterious force that drove it. Most theories point to a hypothetical energy field called the inflaton, which powered the universe's exponential expansion before fading away. But the inflaton's properties, its strength, its duration, even how it decayed remain shrouded in mystery. The voids might hold the answers. Their size, shape, and distribution could act as a cosmic tuning fork, resonating with clues about the inflaton's behavior. And then there's the multiverse angle. Some models suggest inflation never truly ended. It just stopped in our pocket of the cosmos, while other regions continued expanding indefinitely. In this scenario, our universe is one bubble in a frothy sea of disconnected realities, and the voids might be the scars where neighboring bubbles nearly collided. It's a dizzying thought. The great nothingness between galaxies could be the closest we'll ever get to evidence of other universes. What's certain is that these empty regions are anything but barren. They're time capsules preserving the universe's most explosive moments in their silent expanse. Every void is a window, not just into the cosmos as it is, but as it was a fleeting instant after everything began. And as we learn to read their subtle language, we might finally decode the story of our origins, written in the gaps between the stars. Multiverse theories stretch the imagination to its limits, proposing that our universe is just one page in an infinite cosmic library, and the empty zones might be the spines between those volumes. Imagine a soap bubble floating in a froth of others, each containing its own physics, its own stars, its own version of reality. Where these bubbles nearly touch, their membranes could warp, creating regions where gravity behaves unpredictably. That's the radical idea some physicists are exploring. The voids between galaxies might not just be empty, they could be cosmic shorelines lapped by the tides of other universes. The math behind this is as elegant as it is speculative. In certain brainworld models, our universe exists as a three-dimensional brain floating in a higher dimensional space. Nearby brains' other universes could exert gravitational influence on ours, warping space-time in ways that mimic dark energy's repulsive push. In the voids where matter's grip is weakest, this external gravity might dominate, creating pockets where attraction flips to repulsion. It's like placing two magnets near each other, close enough to feel the push but not the pull. The voids in this scenario would be the thinnest parts of our brain, where the presence of another universe is most palpable. But how could we ever test such a mind-bending idea? One clue might lie in the cosmic microwave background. If a neighboring universe brushed against ours during inflation, it could have left faint imprints, anomalies in the radiation's temperature or polarization that resemble scars. Some researchers have already spotted strange, large-scale patterns in the CMB, including an infamous cold spot that defies conventional explanations. Could this be the fingerprint of a collision with another universe? Skeptics argue it's statistical noise, but proponents see a tantalizing thread to pull. Then there's the matter of scale. The largest voids span hundreds of millions of light years, dwarfing even superclusters. If these were boundaries between universes, the sheer size suggests the multiverse's structure is far grander than we've dared to imagine. Picture continents drifting on a planetary ocean. Our observable universe might be just one island in an archipelago of realities, with the voids as the deep channels between them. Of course, this is frontier science at its most speculative. Critics point out that without direct evidence, multiverse theories risk becoming untestable metaphysics. But the voids offer something rare, a potential testing ground. If future telescopes detect peculiar gravitational waves or anomalies in void expansion rates that defy dark energy's predictions, it could hint at forces beyond our universe's borders. Until then, the idea remains a dazzling possibility, one that turns the empty zones from cosmic backwaters into the most exciting frontiers of all. After all, if the universe has edges, they're not where we've been looking. They might be hiding in plain sight, in the great nothingness between the stars. Neutrinos are the universe's most elusive ghost particles, so tiny and indifferent to matter that trillions pass through your body every second without a single collision. Billions more stream unimpeded through planets, stars, even entire galaxies, as if the cosmos were nothing but a faint mist to them. Yet for all their stealth, these nearly massless particles might hold unexpected sway over the emptiest places in existence. If dark energy and hidden dimensions seem like exotic explanations for gravity's reversal in the voids, neutrinos offer a subtler but equally fascinating possibility, that the answer lies not in what's missing, but in what's invisibly passing through. Picture a cosmic game of hide and seek where most players are too big or too slow to avoid detection. Neutrinos, by contrast, are the ultimate hiders. Born in the hearts of stars, supernova, and even the Big Bang itself, they barely interact with anything, making them nearly impossible to trap or study. But in the empty zones where matter is almost absent, their influence might finally become detectable. Normally, neutrinos' gravitational pull is drowned out by the far stronger forces of stars and dark matter. Yet in the voids where those heavier players are absent, even the faintest gravitational nudge from neutrinos could tip the scales. It's like trying to hear a whisper in a crowded room. You'll never catch it over the noise. But step into a silent desert and suddenly that whisper carries. Here's where it gets intriguing. Neutrinos aren't just passive spectators, they're shape-shifters. As they travel, they oscillate between three different flavors: electron, muon, and tau. This chameleon-like behavior means their effective mass changes en route, which could subtly alter their gravitational influence over vast distances. In dense regions, this effect is negligible, but in the voids where neutrinos may be the dominant form of matter, their oscillations might create ripples in spacetime itself, warping gravity in ways we've never accounted for. Imagine a room filled with balloons, each lightly tugging on strings tied to the walls. Normally, the strings stay taut, but if the balloons keep changing size, the tensions shift unpredictably. In cosmic terms, those balloons are neutrinos and the strings are gravity's rules. Then there's the relic neutrino sea, a faint background drizzle left over from the Big Bang, permeating every corner of the universe. These ancient particles are colder and slower than their modern counterparts, but in the voids, their collective mass could be significant. Some theories suggest they might cluster differently in underdense regions, forming invisible clouds that exert a net gravitational push. It's a bit like blowing smoke into a jar. In a crowded space, the smoke disperses evenly, but in an empty one, it might pool strangely, creating unexpected pressure zones. If relic neutrinos behave similarly, they could be the hidden architects of the void's gravitational anomalies. Of course, proving any of this is a monumental challenge. Neutrinos are famously camera-shy, requiring detectors like IceCube, a telescope buried deep in Antarctic ice, to catch the rare few that interact. Mapping their influence in voids would mean sifting through mountains of data for the faintest statistical whispers. But the payoff could redefine physics. If neutrinos are tweaking gravity in the empty zones, it would mean these ghostly particles aren't just passing through the cosmos, they're actively shaping it, stitching invisible patterns into the fabric of space itself. So the next time you hear about neutrinos, remember, they're not just cosmic afterthoughts. In the great voids between galaxies, where the universe's usual rules break down, these phantoms might be quietly rewriting the script. And if we learn to listen, they could reveal secrets far stranger than we've dared to imagine. The next generation of cosmic explorers is gearing up to shine a light on the universe's darkest secrets. Missions like ESA's Euclid and NASA's Nancy Grace Roman telescope aren't just upgrades, they're revolutionaries, armed with technology that could finally decode the empty zone's gravitational rebellion. Euclid, launched in 2023, is already sweeping the cosmos with its razor-sharp infrared eyes, mapping the distribution of galaxies and dark matter across 10 billion light-years. But here's what makes it special: its ability to detect the subtle distortions in starlight caused by voids, like spotting invisible whirlpools in a cosmic river. These distortions, called weak gravitational lensing, might reveal how dark energy warps spacetime in these barren regions. Meanwhile, the Nancy Grace Roman telescope, set to launch around 2027, takes this investigation even further. With a field of view 100 times larger than Hubble's, It'll conduct the most comprehensive survey of cosmic voids ever attempted. Imagine stitching together millions of high-resolution snapshots into a time lapse of the universe's expansion, except instead of watching flowers bloom, we're witnessing the stretching of space-time itself. Roman's specialty, measuring how voids grow over cosmic time, which could tell us whether dark energy's push is getting stronger or if entirely new physics is at play. But these missions aren't working alone. The Vera C. Rubin Observatory, now under construction in Chile, will join the hunt with its decade-long legacy survey of space and time. Starting in 2025, its 8.4-meter mirror will scan the entire southern sky every few nights, catching fleeting changes that might hint at void activity. Think of it as a cosmic motion detector, alerting us to any strange gravitational twitches in the emptiness. Together, these observatories form an unprecedented network, each complementing the others like instruments in an orchestra tuned to unravel the universe's deepest mysteries. What makes this era so exciting isn't just the technology, it's the potential for surprise. Previous missions focused on bright objects like stars and galaxies, treating voids as afterthoughts. Now, for the first time, we're turning our most powerful tools toward the nothingness itself. It's like spending centuries studying islands only to finally train our telescopes on the ocean between them. The data pouring in could confirm existing theories about dark energy's role in voids, or it might reveal something entirely unexpected, like unknown particles or hidden dimensions leaving gravitational fingerprints. The clock is ticking toward discoveries that could rewrite textbooks. Within this decade, we might have definitive answers about whether voids are passive bystanders or active players in cosmic evolution. Every pixel of data from these missions brings us closer to understanding why gravity flips its script in the universe's emptiest corners. And when that breakthrough comes, it won't just solve a niche puzzle. It could redefine our place in the cosmos, showing that even in the great voids, there's far more than meets the eye. The empty zones don't just defy gravity, they shake the foundations of how we perceive reality itself. For centuries, we've clung to the idea that the universe operates by fixed, unbreakable rules. Apples fall, planets orbit, and time flows forward. But these voids whisper a different story, one where the cosmos plays by looser, stranger rules than we ever imagined. If gravity, the force we thought was universal and unchanging, can flip its behavior in these desolate regions, what other so-called laws might bend under the right conditions? Suddenly, the universe feels less like a rigid machine and more like a living, evolving puzzle, full of exceptions waiting to be uncovered. This isn't just about physics, it's about philosophy. The empty zones force us to confront a humbling truth. Our understanding of reality is built on observations from a tiny, biased corner of existence. We've studied gravity where matter is plentiful, on Earth, in solar systems, within galaxies, but the voids remind us that most of the universe isn't like that. Most of it is emptiness, a vast, silent frontier where the rules might rewrite themselves. It's like spending your whole life in a bustling city and assuming every place on Earth is just as crowded, only to step into a desert and realize how much you've missed. The voids are that desert, revealing how little we truly know about the cosmos's full range of behavior. And that raises a deeper question: what is reality, if not the sum of our observations? Science has always been a process of refining models, of replacing old assumptions with new, better-fitting ones. Newton's gravity gave way to Einstein's relativity, which might now give way to something even stranger. The voids suggest that reality isn't a static set of rules but a spectrum of possibilities, context-dependent and fluid. Think of it like language. The word cold means something different in a freezer versus a desert. Similarly, gravity's pull might just be one dialect in a richer cosmic vocabulary, with voids speaking a dialect we're only beginning to translate. This blurring of boundaries extends beyond physics into metaphysics. If the fabric of space can behave so differently in voids, could other fundamental aspects of existence, time, causality, even consciousness also have hidden flexibilities? Some theorists speculate that in extreme environments, like the centers of black holes or the depths of voids, reality might unravel into states we can't yet describe. It's a reminder that the universe isn't obligated to make sense to us. We're the ones catching up, piecing together a puzzle with ever-shifting edges. Yet there's beauty in this uncertainty. The empty zones don't just challenge us, they invite us to wonder. They transform cosmology from a dry catalogue of facts into a living conversation, full of mystery and open questions. Every anomaly, every gravitational defiance is an opportunity to rethink what's possible. That's the heart of science, not clinging to old truths, but embracing the thrill of discovering new ones. So the next time you gaze at the night sky, remember the darkness between the stars isn't just empty. It's a canvas waiting for us to paint it with new understanding. The empty zones between galaxies have inspired wild theories. Some claim they're cosmic portals, others whisper about alien megastructures or hidden dimensions leaking into our universe. While these ideas make for thrilling sci-fi plots, the real story of these voids is far more fascinating than fiction. Let's clear the air. These regions aren't supernatural anomalies or evidence of extraterrestrial engineering. They're natural cosmic phenomena, and their true nature challenges our understanding of physics in ways no fantasy ever could. Take the portal myth, for example. It's easy to see why the idea sticks. Voids are vast, mysterious, and seemingly empty, making them perfect blank slates for imagination. But science reveals something even more extraordinary. These regions aren't gateways to other realms, they're windows into the universe's deepest workings. The gravitational reversals observed here aren't signs of alien technology, but clues about dark energy's grip on spacetime. Imagine thinking a rainbow is a bridge to another world, only to learn it's sunlight bending through raindrops. The real explanation is less magical but infinitely more profound. Then there's the myth that voids are entirely empty. This one's a half-truth. While these regions are staggeringly sparse, they're not perfect vacuums. Quantum fluctuations buzz through them, and faint traces of hydrogen gas weave between galaxies like cosmic cobwebs. Even the emptiest voids we've mapped still contain a few wandering stars, ejected from their home galaxies by ancient collisions. Calling them nothing is like calling the deep ocean barren because you can't see fish from the surface. Look closer, and there's always life, or in this case, physics, in the details. Perhaps the most persistent misconception is that void anomalies disprove Einstein's theories. Headlines love to declare Einstein was wrong when new cosmic quirks emerge. But relativity isn't being overturned, it's being stretched. The voids aren't breaking the rules, they're showing us where the rulebook needs footnotes. Think of it like Newton's laws. They still work perfectly for building bridges or launching rockets, but near a black hole, you'll need Einstein's upgrades. Voids are another extreme environment where our models need refining, not discarding. The danger of these myths isn't just that they're wrong, it's that they distract from the real wonder. The empty zones don't need aliens or portals to be awe-inspiring. Their mere existence forces us to confront how little we know about the universe's scaffolding. When gravity flips its script in these regions, it's not a glitch, it's an invitation to explore deeper, to question broader, and to marvel at a cosmos that constantly defies our expectations. The truth isn't just stranger than fiction, it's more rewarding because it's real. There's something magical about the empty zones, not just because they defy gravity, but because they ignite wonder. Imagine a child staring up at the night sky, not just counting stars but sensing the vast, invisible gaps between them, where the universe itself seems to break the rules. That's the power of these cosmic mysteries. They don't just challenge scientists, they invite everyone, especially young minds, to ask, why? And that question is where every great discovery begins. Take the story of a high school student who stumbled upon a lecture about gravitational anomalies in voids. What started as a passing curiosity became an obsession, leading them to devour books on relativity, dark energy, and quantum physics. Years later, that student is now a researcher, designing simulations to test how dark matter behaves in these enigmatic regions. It's a reminder that the most profound scientific journeys often start with a single spark, a puzzle so compelling it refuses to let go. The empty zones, with their gravitational reversals and cosmic contradictions, are the perfect kindling for that spark. Classrooms and science programs are already catching on. Teachers are using voids as case studies to show students how science evolves, not as a static set of facts, but as a living, breathing process of questioning and revision. Picture a group of middle schoolers debating whether dark energy or hidden dimensions explain the void's behavior, their voices rising with excitement as they defend their theories. These aren't just exercises, they're rehearsals for the future, training the next generation to think critically, creatively, and courageously about the universe's biggest questions. But inspiration doesn't stop at school. Museums and planetariums are bringing the empty zones to life with immersive exhibits. Imagine stepping into a holographic simulation where you can feel gravity's push and pull, watching galaxies drift apart in a void as if you're floating inside one. Or consider citizen science projects that let kids analyze real telescope data, hunting for anomalies in void regions alongside professional astronomers. These experiences don't just teach, they transform abstract concepts into tangible adventures, proving that science isn't confined to textbooks. It's a frontier waiting to be explored. The beauty of the empty zone's mystery is that it's unsolved. Unlike historical breakthroughs wrapped neatly in timelines, this puzzle is alive, evolving with every new observation and theory. That openness is a gift to young minds. It tells them, you could be the one to crack this. Whether it's a teenager scribbling equations in a notebook or a college student coding a new void mapping algorithm, these cosmic riddles are more than just research topics, they're invitations to leave a mark on history. And that's the real legacy of the empty zones. Long before their secrets are fully uncovered, they're already doing something extraordinary, shaping the scientists, thinkers, and dreamers who'll tackle the universe's next great mystery. Because the greatest discoveries aren't just about answers, they're about the people bold enough to chase them. Solving the mystery of the empty zones isn't just a job for one brilliant mind or a single team. It's a symphony of global collaboration, where astronomers in Chile, physicists in Switzerland, and data scientists in Japan all play their part. Picture this: a telescope in the Atacama Desert captures faint light bending around a void, while halfway across the world, a supercomputer in Germany crunches the numbers, revealing patterns invisible to the human eye. Meanwhile, a researcher in India spots an anomaly in the data that sends everyone back to the drawing board. This isn't just science, it's a testament to how humanity's shared curiosity can bridge continents and cultures. The scale of this teamwork is staggering. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, with contributions from over 50 institutions worldwide. Every data point, every pixel of sky observed, is a collective effort, like assembling a cosmic jigsaw puzzle where no single person holds all the pieces. Even rival nations set aside differences when it comes to the voids. Scientists from competing universities and countries routinely share findings because the mystery is bigger than any one lab or nation. It's a rare glimpse of what we can achieve when we prioritize discovery over division. But collaboration isn't just about sharing data, it's about merging disciplines. Astronomers bring their keen eyes for celestial patterns, while particle physicists probe the quantum weirdness that might lurk in the voids. Data scientists, armed with machine learning, sift through mountains of information for hidden clues, like detectives solving a billion-year-old crime. And let's not forget engineers who design the next generation of telescopes and sensors to peer even deeper into the darkness. This isn't just a team. It's an intellectual ecosystem where each breakthrough sparks a dozen new questions, and every answer is built on someone else's work. What's truly inspiring is how this effort extends beyond professionals. Amateur astronomers and citizen scientists contribute too, scanning telescope images for anomalies or running distributed computing projects from their home computers. A high school student in Brazil might flag a strange void pattern that professionals missed, proving that curiosity has no age limit or credential requirement. It's a reminder that the universe doesn't belong to elites in lab coats. It's a puzzle we're all invited to help solve, and the stakes couldn't be higher. If we crack the code of the empty zones, it won't just answer a niche astrophysics question. It could redefine our understanding of gravity, dark energy, and the universe's fate. But here's the beautiful part. No matter who makes the breakthrough, the credit won't belong to one person or country. It'll belong to the collective human spirit, the relentless drive to explore the unknown together. That's the real lesson of the empty zones. They're not just cosmic mysteries, they're mirrors, reflecting our best selves when we work as one. The pursuit of cosmic knowledge carries weight beyond telescopes and equations. It asks us to wrestle with who benefits from the universe's secrets and who gets left behind. Picture a breakthrough. Scientists decode gravity's reversal in the voids, unlocking insights into dark energy. Should that discovery belong only to nations with billion-dollar space programs, or does it become a shared human inheritance? This isn't just philosophy, it's a practical dilemma playing out right now. When the Hubble or James Webb telescopes gaze into the abyss, their data is eventually made public, but the tools to analyze it often remain concentrated in wealthy institutions. It's like handing someone a key but keeping the lock in a vault halfway across the world. Consider the parallels to Earth's history. The age of exploration brought vast knowledge but also exploitation, with indigenous perspectives often erased in the name of discovery. As we map the cosmic web, we must ask, whose voices shape our understanding of these voids? Are we repeating old patterns by prioritizing certain narratives like Western scientific frameworks over others, such as indigenous cosmologies that have contemplated the stars for millennia? Collaborative projects like the Square Kilometre Array Telescope, which involves African nations as equal partners, offer a hopeful countermodel. They prove science can uplift global communities rather than extract knowledge from them. Then there's the question of unintended consequences. Probing the empty zones might seem harmless after all. They're just vast nothingness, right? But what if manipulating gravitational understanding leads to technologies with dual uses? Imagine a future where void-inspired physics unlocks energy sources that could power cities or weapons capable of distorting space-time itself. The same principles explaining why galaxies drift apart in voids might one day be weaponized, turning cosmic curiosity into a security risk. Scientists today face ethical choices akin to those of nuclear physicists in the 1940s, balancing discovery against potential devastation. And let's not forget the environmental cost. Mega telescopes consume vast resources, from energy-guzzling supercomputers to lithium for satellite batteries. Chile's Atacama Desert, home to cutting-edge observatories, also faces water scarcity exacerbated by mining for tech minerals. Does advancing cosmic knowledge justify these trade-offs? Some institutions now offset their footprint with solar-powered facilities or partnerships to restore local ecosystems, but the tension remains. The irony is stark. To study the pristine emptiness of space, we sometimes drain the very ecosystems that let us see the stars clearly. Perhaps the deepest ethical layer is existential. If voids hold clues to the universe's fate, whether it will expand forever or eventually collapse, how does that knowledge shape human purpose? Learning that galaxies might one day be ripped apart by dark energy could inspire unity or nihilism. Scientists and philosophers alike must grapple with how to share such world-shaking truths responsibly. It's not just about data equity. It's about stewarding wisdom that could redefine humanity's place in the cosmos. The empty zones remind us that every discovery ripples far beyond labs and equations. They're mirrors reflecting our choices. Will we hoard cosmic insights or share them as common ground? Will we repeat history's mistakes or forge a new path? The answers won't be found in the voids themselves, but in how we, as a species, choose to reach for them. Art has always been humanity's bridge between the known and the unknowable, and the empty zones of the cosmos have become a canvas for some of the most striking creative expressions of our time. Picture a painter standing before a vast, empty expanse, brush in hand, trying to capture not just the absence of light, but the eerie gravitational defiance of these regions. Some artists use swirling, inverted colors to depict gravity's reversal, as if the canvas itself is pulling the eye outward instead of drawing it in. Others sculpt installations with suspended spheres that seem to repel rather than attract, creating tangible metaphors for the cosmic mystery. These works don't just illustrate science, they evoke the awe and unease of confronting something beyond human intuition, turning abstract physics into visceral emotion. Music, too, has embraced the void's paradoxes. Composers like John Luther Adams have crafted symphonies that mimic the emptiness between galaxies, using sparse, dissonant harmonies to convey the unsettling vastness. One avant-garde ensemble even created a piece where instruments are tuned to frequencies corresponding to the cosmic microwave background's fluctuations, translating the universe's faintest whispers into sound. The result is haunting, a sonic landscape that feels both infinite and intimate, as if the void itself is singing. These compositions don't just describe the cosmos, they invite listeners to feel it, to experience the sublime disorientation of a universe that defies expectation. Literature and poetry, meanwhile, have turned the empty zones into mirrors for human introspection. Science fiction writers imagine civilizations thriving in the voids, their cultures shaped by the absence of stars or the strange physics of their homes. Poets liken the voids to emotional deserts, places of isolation where gravity's reversal becomes a metaphor for life's unpredictability. One striking poem, The Void's Reply, personifies the emptiness as an ancient entity whispering to astronomers, "You call me empty, but I am full of questions you have yet to ask." These creative works don't just reflect scientific curiosity, they expand it, asking how the cosmos shapes not just matter but meaning. Even filmmakers and game designers are drawn to the void's enigmatic allure. A recent indie game, Event Horizon Echo, casts players as explorers navigating a ship trapped in a gravitational anomaly where the usual rules of physics unravel. The game's mechanics, like objects drifting away instead of falling, turn scientific speculation into interactive wonder. Similarly, experimental films use distorted visuals and jarring soundscapes to simulate the disorientation of crossing into a void, making the audience feel the weightlessness and unease firsthand. These mediums don't just tell stories about the cosmos, they let audiences live them, blurring the line between observer and participant. What unites these creative interpretations is their power to democratize cosmic wonder. Not everyone can pass equations about dark energy or gravitational anomalies, but anyone can stand before a painting, lose themselves in music, or be swept up by a story. Art translates the universe's mysteries into a language of emotion, bridging the gap between scientific discovery and human imagination. And in doing so, it reminds us that the empty zones aren't just problems to solve. They are invitations to dream, to question, and to see the cosmos not just as it is, but as it could be. Studying the empty zones between galaxies does more than satisfy cosmic curiosity. It sparks technological revolutions that ripple back to Earth, transforming how we live. When scientists push the limits of observation to probe these vast, mysterious regions, they don't just build better telescopes, they invent tools that reshape industries. Take adaptive optics, for example. Originally developed to counteract atmospheric distortion for clearer views of distant voids, this technology now sharpens vision in medical imaging, allowing surgeons to detect tumors with unprecedented precision. It's as if the quest to map nothingness gave us the ability to see everything more clearly. Then there's the data crunching. Analyzing the faint signals from cosmic voids requires algorithms so advanced they make supercomputers sweat. Machine learning models trained to spot gravitational anomalies in sparse void data are now diagnosing diseases from medical scans, optimizing global supply chains, and even predicting extreme weather patterns. The same code that deciphers the universe's emptiest corners helps farmers predict crop yields or cities manage traffic flow. What began as a tool to study dark energy now lights up solutions to everyday challenges. Even the materials science behind space telescopes trickles down. The ultra-lightweight, ultra-strong composites designed to withstand the rigors of deep space observation have revolutionized everything from aircraft design to prosthetic limbs. A mirror coating engineered to capture the faintest glimmers of void-bound galaxies might now protect your smartphone screen from scratches. The overlap between cosmic exploration and earthly innovation isn't coincidental, it's inevitable. When you're trying to observe the universe's most elusive phenomena, you're forced to invent technologies that push the boundaries of what's possible. Perhaps the most surprising spin-off lies in energy research. The same quantum sensors developed to measure subtle gravitational shifts in voids are now probing underground geothermal reservoirs, helping pinpoint clean energy sources with pinpoint accuracy. Meanwhile, cryogenic cooling systems originally built to keep space telescope detectors near absolute zero are being adapted to make quantum computers more stable. It's a beautiful irony. Studying the coldest, emptiest places in the cosmos might unlock the future of computing right here on Earth. The lesson is clear. Every dollar spent probing the empty zones isn't just an investment in understanding the cosmos, it's a down payment on technologies we haven't even imagined yet. From the algorithms in your phone to the materials in your car, the legacy of void research is woven into the fabric of modern life. And the next breakthrough, the one that changes everything, might be hiding in the data from a telescope trained on nothing at all. The empty zones between galaxies aren't just voids, they're the universe's ultimate deep freezers, where temperatures plunge to just a fraction above absolute zero. Imagine stepping into a place so cold that atoms nearly stop moving, where the very concept of heat feels like a distant memory. At -270 degrees Celsius, these regions are colder than the darkest shadows of Pluto, colder than the Boomerang Nebula, even colder than the afterglow of the Big Bang itself. This isn't just extreme weather, it's the absence of weather, a stillness so profound it defies earthly intuition. But the cold isn't the only extreme. The void's emptiness creates a vacuum 100 times more rarefied than anything we can simulate in labs on Earth. Picture a single hydrogen atom drifting through a space the size of a football stadium. That's the density, or rather the lack of it, in these cosmic deserts. In such thin conditions, sound can't travel, flames can't burn, and even the idea of weather becomes meaningless. There's no wind, no storms, just an endless, silent expanse where the very laws of thermodynamics seem to pause. Yet this extreme environment isn't inert. Oddly enough, the void's frigid emptiness makes it a laboratory for phenomena that would be impossible elsewhere. Take quantum fluctuations, those fleeting particles that pop in and out of existence. In the dense, warm confines of a galaxy, they're drowned out by the noise of stars and gas. But in the void, where matter is almost absent, these quantum whispers become detectable, like hearing a pin drop in a soundproof room. Some theories suggest these fluctuations might even influence the void's gravitational anomalies, as if the fabric of space-time itself is shivering in the cold. Then there's radiation. Unlike Earth, bathed in sunlight, or the bustling center of a galaxy, buzzing with cosmic rays, the void is bathed in an eerie, uniform glow, the cosmic microwave background. This relic of the Big Bang is the only weather the void knows, a faint microwave drizzle that's been cooling for over 13 billion years. It's so weak that a single light bulb emits more energy, yet it's the void's primary heat source, a reminder that even the emptiest places in the cosmos aren't entirely cut off from history. What's most striking about these conditions isn't just their severity, it's how they stretch our understanding of physics. On Earth, we're used to matter behaving predictably. Water freezes at 0 degrees, metals expand when heated. But in the void, where temperatures and pressures hover near absolute limits, matter and energy might behave in ways we've never seen. Could there be exotic forms of ice that only exist in such cold? Could dark matter, invisible and elusive, clump differently in these frigid expanses? The void's extreme climate isn't just a curiosity, it's a testing ground for the universe's most fundamental rules, and that's the real wonder of these desolate regions. They're not just empty, they're extremes incarnate, pushing the boundaries of what we know about heat, cold, and the very nature of existence. Studying them isn't just about mapping the cosmos, it's about discovering what's possible when the universe strips everything down to its barest, most unforgiving essentials. Life in the empty zone seems like a contradiction, a cosmic joke where the universe's most inhospitable places somehow harbor existence. Yet if Earth has taught us anything, it's that life thrives in the unlikeliest corners. From bacteria boiling in acidic hot springs to microbes buried under miles of Antarctic ice, extremophiles have rewritten the rules of where life can survive. So could anything persist in the void's brutal near vacuum, where temperatures hover near absolute zero and gravity itself behaves unpredictably? The answer isn't just about biology. It's a challenge to our very definition of what life requires. Start with the basics. All known life needs liquid water, an energy source, and organic molecules. The empty zones fail spectacularly on the first count. With matter so sparse, water molecules would flash freeze or vaporize instantly, never pooling into the solvent life depends on. Even if some miraculous pocket of liquid existed, The void's extreme cold would slow chemical reactions to a glacial pace, making metabolism as we know it impossible. It's like expecting a campfire to burn in a hurricane. The conditions simply don't allow it. But what if life doesn't play by Earth's rules? Some astrobiologists speculate about shadow biospheres, organisms built from exotic chemistries, perhaps silicon-based or relying on liquid methane instead of water. In theory, such life might endure the void's harshness, drawing energy from cosmic rays or quantum fluctuations rather than sunlight or geothermal vents. Imagine a microbe-like entity that feeds on the faint ripples of spacetime itself, its biology tuned to the void's weird gravitational tides, far-fetched. Absolutely impossible. The universe has surprised us before. Then there's the wild card, panspermia. If life can hitchhike between planets on asteroids, could it also drift between galaxies, carried by rogue planets or interstellar dust? The void's emptiness makes this unlikely, but not unthinkable. A frozen spore, dormant for eons, might survive the journey only to awaken if it someday collides with a molecule-rich nebula or gets captured by a passing star. It's a cosmic Hail Mary, but so was the idea of deep-sea hydrothermal vent ecosystems before we discovered them. The real value of this thought experiment isn't just hunting for void-dwelling aliens. It's about stretching our imagination to recognize life's potential diversity. If we limit our search to Earth-like conditions, we might miss something extraordinary. The voids remind us that the universe operates on scales and timespans we can barely fathom, and life, if it exists out there, might be just as boundless. So while the empty zones themselves are probably lifeless, the questions they inspire could guide us to life in places we've never thought to look. The empty zones may be one of the cosmos' most baffling riddles, but they're far from alone in the universe's catalogue of mysteries. Just beyond these gravitational oddities lie even deeper enigmas, each a thread in the grand tapestry of the unknown. Take dark matter, that invisible scaffolding holding galaxies together. We've mapped its gravitational fingerprints for decades, watching how it bends light and sculpts the cosmic web, yet its true nature remains elusive. Is it an undiscovered particle, a flaw in our understanding of gravity? Every experiment brings us closer, but the answer still dances just beyond our grasp. Then there are black holes, cosmic paradoxes where the laws of physics break down completely. These spacetime ruptures devour light, warp time, and at their cores hide singularities where known mathematics fails. Even stranger are supermassive black holes, lurking at the hearts of galaxies, growing to masses billions of times our suns without any clear explanation for how they formed so quickly after the Big Bang. It's as if the universe cheated its own rules, planting these gravitational behemoths before stars had fully ignited. Don't forget the puzzle of fast radio bursts, brief, intense blasts of energy from distant galaxies, some repeating unpredictably while others vanish forever. Are they the death cries of collapsing neutron stars, signals from advanced civilizations, or something even weirder? Each new detection adds complexity rather than clarity. And then there's the most humbling mystery of all. Why does the universe exist at all? The fine-tuning of physical constants, the precise strength of gravity, the exact mass of electrons, suggests our cosmos balances on a razor's edge. Alter any value slightly, and stars, planets, and life itself would be impossible. Is this cosmic perfection mere chance, or evidence of deeper layers to reality we've yet to uncover? What ties these mysteries together is their defiance of human intuition. They remind us that the universe wasn't designed to make sense to apes who evolved on a rocky planet. Its truths are stranger, grander, and more beautiful than our brains are wired to imagine. Yet that's the thrill of the hunt. Every unanswered question is an invitation to stretch our minds further, to invent new tools, and to keep exploring until the next great revelation pulls back another corner of the cosmic veil. The empty zones between galaxies, where gravity flips its script, stand as cosmic riddles that both humble and exhilarate us. These vast deserts of space-time aren't just gaps in the universe, they're glaring reminders of how much lies beyond our understanding. For every law of physics we've confidently written, these voids scribble question marks in the margins, daring us to rethink what we know. They're not anomalies, they're invitations, pushing scientists to dream bigger and dig deeper into the fabric of reality itself. Consider how far we've come. Just a century ago, we believed the Milky Way was the entirety of the cosmos. Now, we're mapping gravitational reversals in regions so distant their light has traveled billions of years to reach us. Yet with every breakthrough, the universe reveals another layer of mystery. The voids teach us that curiosity isn't just a trait, it's a survival skill for a species determined to comprehend its place in the cosmos. They're like cosmic mirrors, reflecting back not just our ignorance but our potential to transcend it. What makes these regions so thrilling isn't just their defiance of gravity, it's their power to unite. From theorists scribbling equations to engineers designing next-gen telescopes, from students gazing at star charts to artists translating cosmic whispers into music, the mystery of the voids ignites a shared sense of wonder. They remind us that science isn't a solitary pursuit but a collective adventure where every discovery, no matter how small, adds to humanity's grand narrative. And the best part, this story is far from over. The next decade promises revelations we can't yet imagine, as telescopes like Euclid and Nancy Grace Roman peer deeper into the darkness. Maybe we'll crack the code of dark energy, maybe we'll stumble upon physics beyond Einstein's wildest dreams, or maybe, just maybe, we'll uncover something so unexpected it rewrites the rules entirely. That's the magic of the cosmos, it never runs out of surprises. So the next time you step outside on a clear night, let your eyes linger not just on the stars but on the darkness between them. Those empty spaces aren't voids, they're frontiers, waiting for the bold minds who'll illuminate them. The universe isn't finished teaching us, and that's the most beautiful lesson of all.